that you're going to encounter when you do this course is you're going to have to be able to understand that sometimes they'll drop you into a question midway through and say, where does this come from? Now, you all should have received through Remind something that looks vaguely like this, that has these formulas, and these formulas represent different ways and different representations of the same thing. This formula here gives you the formula for slope anywhere along the graph. The answer to something like that would be like y equals 5x, and that formula is used to find the slope anywhere along a graph. You plug in the input, it gives you what the instantaneous rate of change or slope would be. These two representations here are used when you're applying the slope formula at a specific point. So this is telling you to take the change in y over the change in x and narrow it down to get the limit as h approaches 0. But this means I'm approaching 5. This is telling me this answer here would be what the derivative of the function is at 5. This right here, alternate representation, notice how these are similar but different. They're both limits. In this case, it puts the 5 here, here, and here. Because what that is, this is your slope formula. y2 minus y1 over x2 minus x1, except you're taking the limit as x approaches 5, but doesn't equal 5, which means this is the type where you have 5.000001. Something to that effect. You're narrowing in on it to take the instantaneous rate of change. Now take a look at the first one up that we had on your assessment here. You're given that. This is the formula for the slope. This is giving you the instantaneous rate of change at what x value? Hands up, please, if you can tell me. This is giving me the instantaneous rate of change at what x value? Match it to what you have. 5. What is the value of the derivative at 5 going to then be? You've got enough information in front of you. What's the slope or instantaneous rate of change of this g of x at 5? 7. This formula here, and again, if we write it, you write it. This is the formula to determine the derivative of g of x when the x is 5. And we just had somebody tell me, what is the derivative at 5 going to be? 7. Do we know what the g of x function is? Do we need to? You're given enough information there to make that conclusion. Now, what is the instantaneous rate of change at 5? You know it's 7. The slope, the derivative, the instantaneous rate of change. They're all synonymous. They all mean the same thing. You have to be able to get there. The slope of the g of x, the derivative, the instantaneous rate of change, is going to be 7. Now the next one up, this is another representation of this, except it's got stuff plugged into it. This is taking the limit as h approaches 0 of that expression. What do you think the original expression is if the f of x plus h is the cosine of pi plus h? What is the original function that, when you apply the derivative rule to it, you would get that as your output? We got one person who can make that connection. What function, when you apply, when I take f of x plus h, I get cosine of pi plus h? What is this telling me to evaluate out? John, what do you think?
Cosine of pi.
We're trying to evaluate out the derivative or cosine at pi. This is asking you to go through and evaluate out the cosine or derivative at pi. We have the same thing here. Now, here's the other piece that you need to remember. See how this is my f of x plus h? Why is it a 1 here? Because it's cosine of pi. And what's the cosine of pi? 1. Instead of it being f of x, I said it's f of pi, which means the cosine of pi is 1, so they're replacing it with the value. So what is represented there? I go through and say that what's represented there is the derivative of cosine at x is equal to pi. And if you went through, do we know, by the way, what the derivative of cosine at pi is from that expression? No. But you're not being asked that. You're saying what is represented by that. That's a derivative formula for cosine, and there's enough information there to get out what the input value is. Because again, it's telling you the input plus h. And we have to be getting better at pulling out meaning from these expressions. Take a look at the next one. Here's what we're given. By the way, what does this in yellow give us? We know f of 3 is 7. What can I pull out from there? We got one person that can tell me? 2 of you? What does that tell you? What? Yeah, the function, this point is on the graph. And what else do we know? Well, we know this whole mess is given here. Now, what is represented there? What is that telling you? 2 people, 3 of you, put it together. That should start to look familiar now. Close. I can say more than that. The slope at 3 is going to be 2. Sorry, negative 2. Negative 2. That's what that's telling you. It's telling you the derivative at 3 is going to be negative 2. So we need to come up with the equation of a normal line. Who remembers what we said the other day about normal lines? They're perpendicular to the tangent line at the point of tangency. So remember, you could go through, and then that graph of the other day, remember that red line that was coming around? That would be like a perpendicular to that red line at the point that it intersects. So think of this poor graph, right, that's going along. All of a sudden, the tangent line hops on it, and then guess what hops on both the graph and the tangent line? The normal line. So the tangent line touches it once, the normal line goes through it perpendicularly. So it asks us about the normal line here. So what's the slope of the normal line going to be? 1/2. Why is it going to be 1/2? Hands up, please, if you can tell me why that's going to be 1/2. We got one person. Weak. What?
If it's perpendicular, so the slope would be opposite reciprocal.
Yeah.
So if it's negative 2, it would be positive 1/2.
There you go. And you knew that because the way that it was. See how they try to hide it though on you? You've got to be able to make that leap. And if you don't know what those formulas represent, are you able to coherently answer any of this? No. That's why I sent it out to you. While you're driving, you're not allowed to text, but from what I understand, you could sit there on the phone, right, and just look at all of the remind messages that I send you while you're driving. You go, oh, look at that. Oh, a formula, wonderful. Well, I'm just going over the Bay Bridge. I don't need to see much. I know what Irondequoit Bay looks like. I'll look at the formula. It's perfectly legal, from what I understand. You won't veer through any traffic at all. Now, instead of staring at me, how about you go through and give me the equation of the normal line? We'll wait for 8 of you that can tell me what it is. We got 1 so far.
You good, Max?
I'll tell you this, and you'll notice this. Minor foot surgery yesterday, which means I should not be here today, as per my doctor's orders.
You're fine.
You're a trooper.
Stop.
And,
He's only flying out here.
and, oh yeah, wait until I show you about my foot. I've had to change the gauze twice. Very pleasant. I had something wrong with the timing. Now, why am I here? You need me. This is not JV. You are in varsity math. What is the equation of the normal line going to be? No mercy. If you get this wrong, you're standing in the parking lot. Jack? Here's our, what point does it have to go through, Jack?
3.
What point?
3, 7.
3, 7, and it's got to have a slope of what?
-2.
Nope.
1/10.
1/2. Here's our formula. What are you going to get when you use the information you need to use?
Y minus 7 is equal to 1 times x minus 3.
Quantity. You're right. Can you all get there?
Charlie.
We need you there. Now, have your note packets out, please. We're going to start off. We're going to talk today about a bunch of different ways that you can go through and get the derivative and what it represents, etc. But that message that I sent you through Remind, you may want to save in your photos so you have an easy way to go through and recognize what it is. Sure, or you can just, if you hold it down, you got to do what works for you. If you hold down on it, doesn't it give you the option to save it?
Yeah, it does.
Whatever. On iPhone 6 XE Plus, it's got touch receptors. I've got the one, but I know sometimes when I push down on something too hard, like when I get angry at it, all of a sudden a whole new menu comes up that I can get frustrated with. The derivative of a function represents the slope of the tangent line or the instantaneous rate of change. The slope at a point. Those are all things that you need to know. And what is this gold standard of the derivative? It's that formula. That's the definition of the derivative. It gives you an equation for the slope. This equation, let's be crystal clear, is not giving you the slope itself. You'd have to plug the x in. That equation, when you evaluate it out, is going to give you the formula for the slope. We're going to throw some new words at you today. If the derivative exists, we say that the function is differentiable or that it has a derivative. So now we're going to use the definition of the derivative. Find the derivative. Find the derivative, which means I'm not asking for the slope, I'm asking for the equation of the slope given that function. Then use the derivative to find f prime of 3. So I'm going to start off. My derivative of x is equal to, the limit is h approaches 0 of the difference quotient. It's not optional at all. It needs to be shown every time. The shortcut when we get into later units. But the shortcut doesn't work out as nicely anymore. Because this isn't changing. We're not trucking to go through and play Gananda here, are we? Yeah, exactly. I heard that they're going to have EMTs on the sideline, those kids tackle so hard.
So, I didn't play that one.
Now, we need to evaluate this out. What's this going to look like, Mike? What am I going to write out? What's the f of x plus h going to look like?
Quantity of x plus h squared.
Yeah.
Plus 2 quantity of x plus h.
Keep going. That takes care of that. Minus, what's the f of x?
Minus x squared plus minus 2x.
I didn't distribute out. We will in the next step. All of that's up, hanging out over one single h. Now from here, I'm going to go through and blow this up, do as much work as we can. We've got the limit as h approaches 0. Now, up top in the numerator, I'm going to expand out everything that I can. And when I do that, Leah, what's this going to look like?
X squared plus 2xh plus h squared plus 2x plus 2h minus x squared minus 2x.
All over? Boy, I see that I did a lot of work there, and probably you're cramping up a little bit. It might be too much for you. What's the benefit, Steve, of doing all of that work out? So what reductions can we have happen?
The x squares and 2 x's.
All right, so let's get rid of the x squareds are gone. The 2x's are gone. That leaves me with my limit as h approaches, and notice I'm writing it every step until I plug in a 0 in for h. And by the way, at this point, actually, look at what we all have left. You're capable people. What can you do with all of those terms that remain? Hands up, please, if you can tell me that. Yeah. So what's left? You need parentheses around it. You can now go through and evaluate out what the derivative is equal to, because you can now plug a 0 in for h, and Kanji, what do you get as your derivative? So that's the equation of the derivative. We need to then evaluate out the derivative at -3. What is that going to give me, Abby? Well, let's slide this one. Notice we got an equation for the derivative anyway. What's the benefit of using this methodology? You can go through and tell me the slope anywhere along this graph now. What's the slope of this f of x at 1? Hands up, please, if you can tell me. What's the slope of this graph going to be at 1? Hannah, 2? 4. What's the slope of this graph going to be at 3? Sierra? 8. What's the slope of this graph going to be at -1? Valentina? You can do it everywhere. Sometimes it's easier for us to find the derivative of a function at a point. We're going to use a slightly different definition. This one's a little bit awkward, but then again, so are all of you. There's no insults right in math class. You don't even have to pay extra. So now you're going to evaluate out the derivative at -3 directly. So now I'm going to make that replacement in. I'm going to write out the f of x, so the limit as the derivative at a, in this case our a value is 3, is equal to the limit as x approaches what value? Stephanie? The limit as x approaches what value to answer out this example? No? We're finding our derivative at what? -3. So I'm going to take the limit as x approaches -3. Now I need to take f of x minus f of -3 all over x minus -3. Now all of a sudden some parts of this are going to tidy up and clean up quite nicely. Noah, what are you going to fill in the numerator? What is this going to start looking like? I've got the limit as x approaches -3. What's the f of x? And then I'm going to subtract from it f at -3. So what do you get when you take f of -3? So -3 all over. What's your denominator going to be? No, denominator. You gave me the numerator. What's the denominator? What's down in the bottom of this fraction? Yeah, and x plus 3, because it's x minus the input value. So in this case, it's x minus -3, so I get x plus 3. By the way, can I evaluate out this limit right now? No. There's not an h in it, but you can't because the denominator will go to 0, so with the numerator. That indicates something's going to happen, though. Who can tell me something that you want to do now that's going to help us go forward? We got 3, 4 of you. 5. Will this person know? Oh, definitely not gonna know. What are you gonna do? What's the numerator gonna factor down to? Quantity. Oh. Why was that good for us? So now really, what am I left with? Josh? No, that's
Wait.
not what I'm writing out.
A limit of x goes to -3 at quantity x minus 1.
See?
There you go.
And by the way, this is not good. Parentheses around it. The argument of the limit needs to have parentheses around it if it's not a single term. What do we get then? Josh, can you keep going? It sounds like you might have overly exerted yourself to come up with that last answer.
God. X minus 4.
And you're wrong. Who can tell me what the derivative is going to end up being? Yes. Thank you.
You know what I meant.
Yeah, I know. You were wrong.
Well, you don't go by words, you go by what's on the paper.
I'm guessing that was wrong too. Now, we have all of these different ways to denote that we're taking the derivative, and the notation does matter. There's different ways of saying it. We have f prime of x, the derivative of f with respect to x. Y prime, this is when you use this when there's function notation. This is y prime. The problem with this is that you don't know what your input variable is going to be. Your input variable is going to be an x. You're taking the derivative of y with respect to x. That's why it's a dy over dx. The derivative of the function with respect to x is df over dx. And this notation here means the derivative with respect to x of the f of x. If this is our original function, some of you get too marred up in the fact that it's always an f. It's not. If you take the derivative of this, it would not be df over dx, or f prime. It would be h prime of x, or dh over dt. There's a bunch of different ways that you can do it. It's the derivative of h with respect to t. That's how you would denote the derivative of that. The t is the input. Your input is not always an x. Get over it. And then your notation definitely matters. Some of you will find that out when we get our test back, hopefully on Monday. Questions on what we have up? Make sure you have this down. Now, we're going to start doing some pretty cool stuff. Recall from pre-calc that when you analyze a function, you're finding the zeros, looking at where the function was positive and negative and behavior, but this didn't give us an accurate sketch of the graph because we didn't know where the maximums or minimums occurred. We can use calculus to find maximum and minimum points where a function is increasing, decreasing, and constant. Now, what I need you to see is over here, is the function increasing or decreasing? Well, these little lines here are the instantaneous rates of change. What's the slope on that going to be? Negative. When the graph is decreasing, your derivative is negative. So over here, the derivative would be negative. Down here, where it's flat, what is the derivative value going to be? Hands up, please, if you can tell me. What's the derivative of this graph when it's nice and flat? We've got 4 people, seriously? What? 0. And over on the right-hand side, my derivative of the function is going to be positive because the graph is increasing. Can you handle that? Now, we're going to get into some stuff where it's really, really cool. And this is laying a foundation for us to go and take second and third derivatives and you to really analyze graphs. And there is a whole lot of stuff going on. Taking a look, these are 3 different situations. Increasing curves come in 3 different varieties. Describe the rate of change by looking at these along 3 points on the curve. So looking at this graph, is this graph increasing? Well, we'll say this. think about the derivative or the rate of change of this graph. What do we know about it? Hands up, please, if you can describe for me what the derivative along that graph is going to be. You should notice something about it. You take the derivative, I just took it at 3 different values. What do you know about them? What do you know about those derivatives? We got one person who can answer, seriously? 4 of you? 5? Okay. Yeah. So what do you know about the rate of change? Constant. It's increasing at a constant positive rate. All of these graphs have positive slopes. Each derivative, as I go left to right, is exactly the same. Now, is this function, take a look here, what do we know about these derivatives here? I took it at 3 spots. What can you say when you compare them going left to right? They're not constant. We can be more specific than that. They're increasing. So is the function increasing or decreasing as I move left to right? It's increasing, and not only is it increasing, but it's increasing at an increasing rate. Meaning that as I go from value to value, the slope is going up. Exponential functions, as we go out to the right, have this happen. We're increasing at an increasing rate. That's called concave up. Looks like a cup. Concave down looks like a... There we go. Take a look now at the second graph. All of those slopes, all of those lines of tangency are positive. Are they all the same? Who can tell me what conclusion or how you would describe the increasing behavior of that piece? We got 2 people, 3. Noah? There you go. This graph is going to be increasing at a decreasing rate because the slope here is very severe. As we move from left to right, it's leveling off. That's actually called a second derivative. MCC makes you go through. By the way, the AP, who here is interested in taking the course for MCC credit? There's a couple of you that are. Okay, it's up to you what you want to do, but you have to go to, and I'll try to share a link through Google Classroom, but I think that the registration closes soon. Oh, actually, you know what? I even forgot. Here, before you leave today, I've got to remember how to get that. I'll go and look and see if they have the Xerox scholarship form. I love it. They give us 400 of these dual enrollment forms. Right? Now, here's the stuff. Before you leave today, pick up an index. Those of you that are interested in the MCC dual credit, over here tells you how to enroll. Over here, if you got above an 83 in pre-calculus, you're able to take this for dual credit. I advise you and caution you, if you want to take it, terrific. Know what your colleges take. Call the school. Actually, call the schools that you're interested in going to. Right? McDonald's University does take it as a credit, for those of you who are interested. All right? Now, what is true about the slopes of the tangent lines anywhere along these curves? What do all of them have in common? What do all the tangent line slopes have in common? Hands up, please, when you can tell me. What do all of these tangent line slopes have in common? Seriously, 2 people? Look out, RPG. What do you want to say? Close. Well, yeah. I was going to say that they're all positive. So we can conclude. Here's our big summary statement. If the derivative is positive, the graph is increasing. Now, decreasing curves come in 3 varieties, as shown there. Describe the change. Well, what would we say about the decreasingness of the first graph? We got 1 person. What can we say about the decreasingness of it, Steve? Terrific. What can we say about the decreasing that's happening in the second one? Adam?
Decreasing at an increasing rate?
No, because see your slope here would be like negative 15 and here. It's leveling off. Take a look at the next one. Jake, what would you say about that? There you go. What is true about the slope of the tangent line anywhere along these decreasing curves? Hannah, 1? What conclusion can we make then? Who can tell me what conclusion? 1 person, 2 of us, 3, 4. Cam, what do you say? Questions on that? This is the stuff that's really going to be a push for you. If the function is increasing, what's the tangent line going to look like? Hands up, please, and describe for me what the tangent line is going to look like if the function is increasing. You can describe it. You think it works. 1 person. What do you want to say? Yeah, it's going to have a positive slope. So I'm going to sketch that tangent line, and it's going to look like this. What do you know about the derivative values if it has a positive slope? The derivative itself is going to be positive. What about if the function is decreasing? What do we know about the tangent line? Hands up, please, if you can tell me. Steve? It's going to have a negative slope, which means it's going to drop down like that, and the derivative of it would be negative. If it's constant, the tangent line is going to go straight across, and the derivative would be equal to what? Hands up, please, if you can answer that. 0. Now, watch what we do to go from the graph to the graph of the derivative. So again, keep this in mind. Here is my function. Here is my derivative. Now, you're going to be doing tasks in here that ask you to build the derivative graph from the function graph. The first thing that I always do is sketch any max and min candidates, or anywhere where this tangent line is going to have a slope of 0. Look at the original function. Hands up, please, when you can tell me at what x values will this graph have a horizontal line of tangency. I've got 1 person, 2. I need the x values where this graph is going to have a horizontal line of tangency.
-3, 2, and 4.
-3, it's got 1. 2, it's got 1. 4, it's got 1. And you're missing 1. -1. Now, looking at the graph of the derivative, what's the slope of the derivative going to be there? 0. So when I'm graphing this out, what is the slope at -3? 0. What's the slope at -1? 0. What's the slope at 2? So I go over to 2 and I plot out the point 2, 0. What's my slope at 4? 0. And this takes, in all honesty, it took me like a full semester to really be able to build and see this relationship. And if you're not doing it constantly, you're going to lose this skill, at least for me. What is the graph doing here? Well, I'd say I'm looking at this piece from here to here. What is the graph, or what is the slope of the graph going to be? Hands up, please, if you can tell me. Negative. So what values would I be plotting over here? Where else is this graph going to be negative? Hands up, please, if you can tell me where else it's going to be negative. From where to where? Where else does this graph have a negative slope? We got 4 people. From -1 to 4. So notice what happens. From -1 to 4, where does the graph reside? Below the x-axis, which means the y values are negative. Now, where is this graph positive? From negative 3 to negative 1. So this graph is positive. It's also positive here, which means it rises above here. Questions on this? It's complicated stuff. Why, is it too easy, John?
What?
Is it too easy for you?
No.
All right.
It's just fun.
Came in for this. Now, we're given that f of negative 1 equals 4. F is continuous for all x, and the graph of the derivative is shown. Graph out the function. This right here is my derivative graph. This right here is my function graph. I need to build that graph. What is one thing that we need to know and plot out immediately? Who can tell me one thing that I need to plot out right away? We've got one person. Look out Princeton. Look out Yale. 2 of us? Oh, come on. Come on. Leah? Let's plot the point negative 1, 4. So go back 1, go down to negative 1, 2, 3, 1, 2, 3, 4. So I know that point is on the graph. Now, what is the slope of this graph at negative 2? Who can tell me? What's the slope of the graph at negative 2? Negative 1. What's the slope of the graph at negative 3? Negative 1. What's the slope of the graph at negative 5? You got to do rise over right to get the other points on this graph. So we know it starts off at... So to get to the next point, my slope would be negative 1. So I go up 1, back 1, that's negative 1. Negative 1 again, negative 1 again, negative 1 again, negative 1, and I keep going. Does the left half of that graph have a constant slope of negative 1? Who can describe to me what's happening on the right half of this graph? Hands up, please, if you can tell me what's happening on the right half of this graph. We got one person. 2, 3. Noah?
It's going to be increasing with the slope of 2.
Is the slope changing? Does the slope of this graph change?
No.
No. It's constant. What's the slope always going to be? 2. So rise over right means 2 over 1, 2 over 1, 2 over 1, 2 over 1, 2 over 1. Now I'm going to build the graph. Now some of you who are more astute are going to say, what didn't we deal with yet that's on there? Whoa, that second piece was terrible. Hands up, please, if you can tell me what we didn't deal with yet that's on that graph. Yeah, what does that hole represent? Well, what is the derivative or slope at negative 1 going to be? Look at the graph of the derivative. What's the slope at negative 1? It doesn't exist. Look at the graph. Why doesn't the slope at negative 1 exist? It's a corner. You could draw a line of tangency like this. You could draw one potentially like that or like that. You can't get one. Now, here's the part where it's going to be awkward for us. Go in. You all should have your calculators. Did you all? All right, now you can sign in. We need you all to do that, and we're going to walk our way through. I've never been able to successfully use these to graph, so we're going to find out together, but Ms. Miller knows that I'm a little bit limited, and she gave us a ton of directions, so hopefully we can figure it out. Make sure that we're in a document so everyone is signed into their calculator. let's go in. Again, you do not ever work in the scratch pad. You're always going to work in the document. So let's start this off. You're going to go into the grapher, and we're going to start off. It looks like our first directions tell us to go through and enter the function in there. So let's do, what did we do? Let's actually do the x squared plus 2x one, the one that we did in the beginning. So go in, please, and enter the function in the graph entry line. So did we do that? Let's see. Whomever this is, you're our guinea pig. X squared plus 2x. All right, now, hit enter. The next thing that you're going to do is, so that's our function. Now, what should the graph of the derivative look like? Well, it's actually going to look like a line because down here it's decreasing at a constant amount. It's going to cross the x-axis here, and then it's going to be positive. So our derivative should look something like this, because everywhere to the left of the minimum, it's negative. Everywhere to the right of the minimum, it's positive. Now go in and let's add a new entry line, so I think it's a Control T. And then you're going to press Control, or whatever. Now press this here. Nope, delete that, not Control that, sorry.
No.
Hit this button here. Enter, go and do the derivative, which is right here. The one that's highlighted up there. Oh, we missed it. Go back. Back one more, that second derivative. There's the first one. So the derivative with respect to x of, so put an x down there, of, what's our function? X squared plus 2x. No, careful, we're too high up. Plus 2x. Hit enter. Is this going to graph? Fingers crossed. There you go. It's just like we said it was going to be. Just like we said it's going to be. Questions on that? Let's bounce over to the next page and just add on our notes for today.
I think we're done for today.
Now, you're done for today. Let's go back to the front of our notes and let's see what we need to anticipate coming up. All right. So today is 9:30. Next time we have class, there is a small quiz on the derivative, recognizing what's there. I know. You know what we should do? We should just go through and not have any tests or quizzes, only interpretive dances of things that we know. We'll go through and say, oh, I want you to give me a finger painting of what a derivative makes you feel like inside. And then we'll do then we'll do test corrections, and then we'll go through, are you nuts? I'm dealing with the same thing now with these poor little kids in L2. They've had all these test corrections, all of these fluff grades. Are you nuts? Everyone that I have scores higher on the read. Your fluff grades are your quizzes.